On the afternoon of the 19th of June, 1826, in a second-floor workroom in the village of Saint-Loub de Varens in eastern France, a retired military officer named Joseph Nickfor-Nunti, Pisse, removed a pewter plate from the back of a camera obscura and held it up to the light. The plate had been sitting in the camera for somewhere between 8 hours and several days. Nouri Pisse himself was never entirely precise about the duration, and it had been coated with a thin layer of bitumen of Judea, a naturally occurring petroleum tar that hardens when exposed to light. Where the sunlight streaming through the camera's lens had struck the plate most intensely, the bright sky, the illuminated walls of the buildings outside his window, the bitumen had polymerized and become insoluble in the lavender oil he used as a solvent. Where the light had been weak or absent, the shadows, the dark roof tiles, the bitumen remained soft and was washed away, revealing the darker pewter surface beneath. What remained was a faint, ghostly, barely legible image of the view from Nouri Pisse's upstairs window, a courtyard, a pigeon house, a barn roof, a tree, and a patch of sky. It was the first photograph. That image still exists. It is held in the Harry Ransom Center at the University of Texas at Austin, preserved under inert gas in a climate-controlled case, and it looks almost nothing like a modern photograph. The tonal range is compressed, the details are blurred by the long exposure, and the lighting is peculiar because the sun moved across the sky during the hours. The plate was exposed, illuminating both sides of the courtyard simultaneously. But it is a photograph in the fullest physical sense of the word, a record made by light, inscribed by photons, onto a material surface through a chemical reaction driven by electromagnetic energy. Every photograph that has ever been made since, every daguerreotype, every albumin print, every roll of Kodachrome, every digital image captured by a CMOS sensor in a smartphone operates on the same fundamental principle. Light from a scene enters a lens, is focused onto a recording surface, and produces a pattern that corresponds, through whatever chain of physical and chemical intermediaries, to the spatial distribution of brightness and color in the original scene. But here is the part that Nouri Pisse could not have known, because the physics that explains it would not be developed for another 80 years. The light that entered his camera and exposed that pewter plate did not stop at the plate. The vast majority of the photons reflecting off the courtyard outside his window, the photons that collectively constituted the visual scene, the image of the pigeon house, and the barn and the tree, were not captured by his camera at all. His lens gathered light from a tiny solid angle, a cone of perhaps a few degrees, and focused it onto a plate a few inches across. The rest of the light, the overwhelming majority, continued outward in every other direction, passing through the air, through the glass of other windows, reflecting off other surfaces, scattering off dust particles and water droplets, and for the fraction that was directed upward through the atmosphere at wavelengths where the air is sufficiently transparent, leaving the Earth entirely and entering the vacuum of space. Those photons are still traveling. At the speed of light, they have now covered a distance of approximately 199 light years, forming an expanding spherical shell of electromagnetic radiation that carries, encoded in its spatial structure, a faint and degraded but physically real representation of the view from Nouri Pisse's window on that summer afternoon in 1826. This is not a metaphor. It is not poetry dressed as science. It is a direct consequence of the wave nature of light, the inverse square law, and the stability of photons in vacuum. And each of these physical principles has been tested with extraordinary precision. A photon emitted from a surface, whether that surface is a sunlit courtyard in Burgundy, a child's face at a birthday party, or the screen of a phone displaying a selfie, travels in a straight line through vacuum at 29.792.458 meters per second until it interacts with matter. If it does not interact with matter, it continues indefinitely. There is no friction for light in vacuum. There is no drag, no decay, no gradual diminishment of the photon itself. The intensity of a light beam decreases with distance because the photons spread out over an ever larger sphere, the inverse square law, but each individual photon retains its energy and its identity. It does not slow down. It does not fade. It does not expire. From its own reference frame, as special relativity demands for any massless particle traveling at the speed of light, no time passes at all between its emission and its eventual absorption, wherever and whenever that absorption might occur. The implications of this for photography are both staggering and, upon reflection, inescapable. Every scene that has ever been illuminated by light, every scene has scattered photons into every direction in the hemisphere above it. The vast majority of those photons were absorbed by the local environment within meters or centimeters of their emission, captured by walls, floors, clothing, skin, leaves, water, dust. But a fraction escaped. Through windows, through open doors, through gaps in canopy cover, through the atmosphere itself. The Earth's atmosphere is not perfectly opaque. At visible wavelengths, roughly 380 to 700 nanometers, the atmosphere transmits a substantial fraction of incoming and outgoing radiation, with losses due primarily to Rayleigh scattering, which preferentially redirects shorter wavelengths and gives the sky its blue color, and to absorption by water vapor, ozone, and aerosols. On a clear day, looking straight up through the atmosphere, the optical depth at visible wavelengths is approximately 0.3, meaning that roughly 74% of the light directed straight upward makes it through to space. At angles closer to the horizon, the path length through the atmosphere increases and the transmission drops. But even at moderately low elevation angles, a significant fraction of visible light escapes. This means that every outdoor photograph ever taken, every landscape, every street scene, every portrait shot in natural light, every image of a building or a mountain or a field, was accompanied by the escape of photons from the same scene into space. The camera captured a few of them. Space received the rest, and the photons that reach space carry the same information as the ones that reach the camera, because they originated from the same scattering and reflection events at the surfaces of the same objects. A photon that bounced off a child's red jacket and entered a camera lens is physically identical in its information content to a photon that bounced off the same jacket at a slightly different angle and sailed upward into the sky. Both photons carry the wavelength signature of the dye in the fabric, modified by the illumination spectrum of the ambient light. Both were emitted at the same instant. Both traveled at the same speed. The only difference is their direction, and therefore their fate. The photons that entered the camera were absorbed by silver halide crystals in film, or by silicon photodiodes in a digital sensor, and their energy was converted into a latent chemical image, or an electrical signal that was subsequently processed, stored, and displayed. Their journey ended at the focal plane. The photons that escaped into space began a journey that has no predetermined end. They joined the expanding shell of electromagnetic radiation that the Earth has been emitting since it first had an atmosphere and a surface capable of reflecting sunlight. A shell that now extends roughly 4.5 billion light years in radius for the oldest photons and mere light. Seconds for the most recent, growing at the speed of light in every direction, carrying an inconceivably complex, hopelessly scrambled, but physically real record of every optical event that has ever occurred on the surface of this planet. The concept of this expanding light shell is not new. It has been discussed in various forms since at least the early 20th century, and it forms the conceptual basis for the recurring science fiction scenario in which a sufficiently advanced telescope, positioned at an appropriate distance from Earth, could look back and observe historical events as they happened. The idea is appealing, and it is technically grounded in real physics, but the practical barriers to actually reconstructing an image from these photons are so formidable that they deserve careful examination, because the gap between the photons exist and the image can be recovered is not merely large. It is, by any reasonable engineering standard, infinite. The fundamental problem is the inverse square law. When photons radiate from a point source into free space, they spread out uniformly over the surface of an expanding sphere. The number of photons passing through any fixed area, say the aperture of a telescope, decreases as the square of the distance from the source. A scene that scatters a certain number of photons per second, per steradian into space will deliver, to a telescope of aperture area A at distance d, a number of photons proportional to a divided by d squared. For a terrestrial scene at human scales, the number of photons scattered is large, but not unlimited. A reasonably well-lit outdoor scene on Earth reflects roughly 10 to the power of 19 photons per second, per square meter of surface area into the upward hemisphere. This seems like an enormous number, and at close range it is. But spread those photons over the surface of a sphere with a radius of, say, 1 light year. about 9.46 trillion kilometers, and the density drops to roughly 10 to the minus 8 photons per s-econd per s square meter. At 10 light-years, it drops to 10 to the minus 10. At 100 light-years, 10 to the minus 12. At 1,000 light-years, 10 to the minus 14. To collect even a single photon from a specific square meter of the Earth's surface at a distance of 1,000 light-years would require a telescope with an aperture of roughly 10 to the 14th square meters, about the area of the state of Virginia, collecting for a full second. To reconstruct anything resembling an image with millions of pixels, each requiring thousands of photons for a reasonable signal, to noise ratio, the telescope would need to be larger than the Earth, possibly larger than the solar system, and it would need to collect light for years or centuries. And this assumes that the photons arrive unperturbed, which they do not. Even in the vacuum of interstellar space, the light encounters obstacles. Interstellar dust, microscopic grains of silicate and carbonaceous material, typically a fraction of a micrometer in diameter, scatters and absorbs optical photons, particularly at shorter wavelengths. The interstellar extinction in the visible band is roughly 1 magnitude per kiloparsec in the galactic plane, meaning that the intensity of light is reduced by a factor of roughly 2.5 for every 3,260 light-years of travel through the disk of the Milky Way. Over longer distances, particularly through the dustier regions near the galactic center, the extinction can be much higher. The photons that carry the image of your family vacation are not traveling through a perfect vacuum. They are traveling through a thin but real medium that slowly erodes the signal, scattering some photons out of the beam, absorbing others, and replacing the original spatial information with noise. Beyond the dust, there is diffraction. The angular resolution of any imaging system is limited by the ratio of the wavelength of light to the diameter of the aperture. This is the diffraction limit, expressed by the Rayleigh criterion. To resolve a detail 1 meter across at a distance of 1 light-year would require a telescope with an aperture of approximately 5.6 million kilometers at visible wavelengths, roughly 4 times the diameter of the Sun. At 10 light-years, the required aperture scales up to 56 million kilometers. At 100 light-years, 560 million kilometers. These are not engineering challenges that can be overcome with better technology. They are consequences of the wave nature of light itself, as fundamental as the speed of light or the charge of the electron. So the image, in any practical sense, is unrecoverable. The photons exist, but the information they carry has been diluted below any conceivable threshold of detection by the remorseless geometry of the inverse square law, degraded by interstellar scattering, and blurred beyond recognition by the diffraction limit. No telescope that could be built by any civilization, no matter how advanced, could reconstruct the image of a face or a building or a landscape from the photons that left Earth at the moment the photograph was taken, not without violating the laws of physics as we currently understand them. And yet the photons are still there. This fact, however practically useless, is physically non-trivial. Each photon in the expanding shell is a quantum of the electromagnetic field, a particle with a definite energy, momentum, polarization, and phase, properties that were determined by the physical event that produced it. A photon that was reflected from a green leaf carries a wavelength centered around 550 nanometers because chlorophyll absorbs red and blue light and reflects green. A photon that bounced off a human face carries a spectrum shaped by the absorption properties of melanin, hemoglobin, and keratin in the skin. A photon that was emitted by a camera flash carries the broadband spectrum of a xenon discharge tube, modified by whatever it illuminated. These are not abstract quantities. They are measurable physical properties that encode, however indirectly, information about the objects and events that produce them. The photons do not know what they represent, but they carry, in their quantum states, a physical trace of their origins that no subsequent process, short of absorption, can erase. The question of what constitutes a photograph then takes on an unexpected dimension. In the conventional understanding, a photograph is an object, a print, a negative, a digital file, that records and stores an image. The record is static. The image can be viewed, copied, and preserved. But the physics reveals that the original optical event, the pattern of light that the camera captured, was never confined to the camera. It radiated in all directions. The camera intercepted a tiny fraction of it and made a permanent record. The rest continued outward, uncaptured but not destroyed. In a strict physical sense, the scene itself, the pattern of photons reflecting off every surface, is still propagating through space, growing fainter and more diffuse with every passing second, but never reaching zero, never being erased, never ceasing to exist as long as the individual photons remain unabsorbed. This leads to a thought that is less about physics and more about the nature of images and memory, though it remains grounded in physical fact. Every moment of your life that occurred in the presence of light, which is to say, virtually every moment, produced an expanding shell of photons that encoded the visual scene. Not just the moments you chose to photograph. All of them, the light reflecting off your face as you sat at the breakfast table this morning, is now roughly 16 billion meters from Earth, a shell of radiation expanding at the speed of light into the interstellar medium. The light from the afternoon you spent at the park when you were 7 years old has traveled roughly 30 to 40 light years, depending on your current age, and now forms a shell that has passed dozens of star systems. The light from the last time you saw a person who has since died is somewhere between these extremes, expanding outward, carrying the optical information of that final meeting, encoded in the wavelengths and angles and polarizations of photons that will never return to Earth. None of this information is accessible. None of it can be retrieved. The photons are too dispersed, too faint, too scrambled by their passage through the interstellar medium. But the fact of their existence raises a question that physics can pose but cannot answer. Does it matter that the information exists if no one can read it? The photon carrying the reflected light of your grandmother's face is physically real. It is traveling through space at this moment. It has not been destroyed. It has not decayed. The information it carries, a single data point in what would need to be a billions of pixels image to be meaningful, is preserved in its quantum state with perfect fidelity, minus the cosmological redshift that gradually stretches its wavelength as the universe expands. In a universe governed by unitary quantum mechanics, this information is conserved. It cannot be erased. It can only be dispersed, entangled, made practically inaccessible, but never annihilated. The light from every photograph and from every unphotographed moment persists. The cosmological fate of these photons mirrors the fate of all light in an expanding universe, and it has been worked out in considerable detail by astrophysicists studying the long-term evolution of the cosmos. As the universe continues to expand, driven by dark energy, the wavelength of every photon in the intergalactic medium is stretched in proportion to the scale factor of the universe. A photon emitted at 550 nanometers, green light, the peak sensitivity of the human eye, will, after sufficient cosmic expansion, be redshifted into the infrared, then into the microwave, then into the radio, its wavelength growing without limit, its energy diminishing towards zero but never reaching it. The photon remains a photon. It does not decay. There is no mechanism in the standard model of particle physics by which a photon in vacuum can spontaneously disappear, because there is no lighter particle it could decay into while conserving energy and momentum. The photon's stability is not an approximation or an assumption. It is a theorem, derivable from the symmetries of quantum electrodynamics, specifically from the gauge invariance of the electromagnetic field and the masslessness of the photon itself. Over timescales that dwarf the current age of the universe, these photons will continue to propagate through an increasingly empty, increasingly cold, increasingly dark cosmos. The stars will have burned out. The stellar remnants will have cooled. The black holes will have evaporated. The protons and neutrons in the remaining matter will have decayed, if grand unified theories are correct, into positrons, pions, and photons. And eventually, the universe will contain nothing but photons, neutrinos, and a thin scattering of electrons and positrons, all drifting through a space-time that is expanding exponentially, all redshifting toward longer and longer wavelengths, all carrying, in their quantum states, the faintest conceivable traces of the physical processes that created them, including, somewhere in that unimaginably vast and featureless expanse, a handful of photons that were once reflected from a pewter plate in a second-floor workroom in the village of Saint Loup de Varens, and a handful that bounced off your face this morning as you glanced at your phone. The physicist and mathematician Freeman Dyson, in a celebrated 1979 paper titled Time Without End, considered the question of whether life and information processing could continue indefinitely in an ever-expanding, ever-cooling universe. His analysis, while optimistic in some respects, ultimately confronted the same thermodynamic limits that constrain all physical processes as the available free energy decreases and the temperature of the cosmic background radiation drops towards zero. The cost of any computation, any thought, any observation, any act of memory increases without bound. Eventually, the energy required to process a single bit of information exceeds the energy available in the observable universe, and information processing ceases. Not because the information has been destroyed, but because there is no longer any physical system capable of reading it, interpreting it, or doing anything with it. The information persists, the meaning does not. This distinction between the persistence of information and the persistence of meaning may be the most important thing the physics of light can teach us about photography, about memory, and about the human desire to preserve moments against the erosion of time. A photograph, in its conventional form, is an attempt to fix a moment, to arrest the flow of photons reflecting off a scene at a particular instant and trap them in a static record that can be revisited. The act of taking a photograph is, in this sense, an act of selection, choosing which fraction of the outgoing light to capture and preserve, and implicitly accepting that the rest will be lost. But the physics reveals that nothing is lost, not really, not in the strictest physical sense. The uncaptured light continues to travel. The scene continues to radiate into space. The moment is not fixed in the photograph. It is fixed in the expanding shell of photons that the photograph sampled but did not contain. The photograph is a souvenir. The light is the thing itself. There is something both humbling and strange in this realization. The photograph in your hand, or on your screen, is a reduced, compressed, two-dimensional projection of a single instant's worth of photons, captured by a tiny aperture and frozen in pigment, or pixels. The full optical event, the complete pattern of light that constituted the scene, was vastly larger, richer, and more information, dense than anything a camera could record. It included photons at every wavelength from ultraviolet to infrared, traveling in every direction from every surface, carrying information about texture, depth, material composition, temperature, and motion that no single photograph could possibly encode. And all of those photons, except the tiny fraction absorbed by local matter, are now in space traveling outward, forming an ever-expanding, ever-fainter, but ever-present record of the moment. The photograph preserved a cross-section. The universe preserved the whole. Whether this constitutes a meaningful form of preservation depends entirely on what you mean by meaningful, and physics has nothing to say on that subject. The photons do not care whether they are meaningful. They propagate because the equations of electrodynamics say they propagate. They persist because the conservation laws say they persist. They carry information because the quantum mechanical description of their emission event is encoded in their state vector, and unitary evolution preserves that encoding for all time. These are facts about the physical world, established through centuries of experiment and mathematical analysis, and they are not in dispute. What is in dispute, or rather what lies permanently beyond the reach of physics to resolve, is whether it matters that the light from your child's first steps is still traveling through the Oort cloud, or that the light from the last photograph of a demolished building is now 7 light, years out, and passing through the neighborhood of Wolf 359, or that the light from every wedding, every funeral, every ordinary Tuesday afternoon in the history of human civilization is out there, right now, expanding into the galaxy at 299792458 meters per second, unseen and unseeable, but stubbornly, irreducibly, physically real. Perhaps the most honest thing that can be said is this: the universe does not take photographs, but it does not need to. Every event that occurs in the presence of light automatically generates its own record, scattered in all directions at the maximum speed the laws of physics allow, preserved by the conservation laws that govern every quantum interaction, and destined to persist for as long as the cosmos itself endures. The camera is a convenience, a device that concentrates this information into a form that human eyes and human brains can interpret. But the information itself was never confined to the camera, and it was never at risk of being lost. Not in the way that a hard drive can be lost, or a shoebox of prints can be destroyed in a fire. The physical record of every illuminated moment is woven into the fabric of the expanding universe, carried by photons that are older now than the moments they represent, and that will outlast every structure, every memory, every civilization, and every star. The photograph on your wall will yellow and fade. The file on your phone will be corrupted and deleted. But the light that made the image, the original light, the reflected photons that were scattered into space at the moment the shutter clicked, will still be traveling when the last red dwarf gutters and dies, when the last white dwarf cools to the temperature of the void, when the universe itself has expanded into a darkness so vast and so empty that the word universe no longer describes anything that a mind would recognize. The light does not know what it carries. It does not remember the face, the landscape, the afternoon. It simply travels because that is what light does. The one thing it has always done, the one thing the equations have always said it would do, from the first photon emitted in the hot plasma of the early universe to the last photon that will ever be reflected from the last surface of the last object in the cosmos. It carries its information not as a message, but as a scar, a physical imprint left by the interaction that created it, indelible and permanent and utterly indifferent to whether anyone, anywhere, at any point in the future, will ever know what it means. And in that indifference, there is a kind of permanence that outlasts every other form of record, keeping that human beings have ever devised. Not the permanence of stone, which weathers, not the permanence of writing, which can be burned, not the permanence of digital storage, which decays, the permanence of light, which moves at the maximum speed permitted by the structure of space-time, which does not age, which does not stop, and which carries in the vibration of its electric and magnetic fields the last physical evidence that a moment ever happened, traveling outward at 300,000 kilometers per second, into an emptiness that it will never fill, bearing a record that no one will ever read, but that the laws of physics will never permit to be erased.